theme running through this and running through, I suppose, like the last 20 years of my life really, has been exploring what I can best describe as sonic systems. So thinking in digital terms and in biological terms and in musical terms about approaches to composing and decomposing these systems. So another subtitle might be, what can experimental musicking learn from ecosystems, and how might experimental computer musicking help save the planet? That's what we're going to come back to. So my work sits at this sort of intersection between music, ecology, more and less abstract ecology, and technology. So some of the work I'll talk about early on was thinking about performance and computer music and interactive generative arts, and how we might learn from real-world biological systems, particularly ecosystems, to kind of make better art, whatever that might mean, and we'll talk about what that means. And then my work for the last sort of 5 years has kind of flipped around and said, well, how actually can some of the things that we are au fait with, some of the techniques that we're familiar with in music technology and across machine listening and machine learning, be applied to some very real world problems in ecology, namely biodiversity monitoring. And that'll be the main focus of my talk this morning. But as I say, you're all quite a multi-threaded lot, so I wanted to put all of that in context so you got an idea of where I've come from, because some of these other things might be things that I might like to talk to you about. So I grew up playing music. I'm a cellist. I grew up in very sort of informal musical setting, basically playing chamber music in goat sheds at the weekends and in summer holidays. So music, and particularly chamber music, ensemble performance, has always been a really core part of my life and my mind and my social interactions, if you like. And although I haven't ever studied music formally, I'm now teaching the music department, but I never studied music formally, but it's been a kind of core thread throughout all of my work. So my PhD, I studied evolutionary adaptive systems at Sussex, which is kind of like artificial life boot camp. So neural networks and adaptive systems, cybernetics, evolutionary systems, evolutionary robotics, understanding evolution in the abstract. So the small problems like the origins of life, what is consciousness, this kind of thing. And it was a setting where people were very much of anti-representationalists. So thinking isn't computation, thinking is being in the world. So a lot of foundational thinkers in contemporary inactivism, thinking about mind and life as a continuum, this kind of environment. And playing with, I developed a kind of Ross Ashby fetish in working with homeostats and these kind of adaptive dynamical systems, and just found them really alluring and thought, well, I was totally naive to computer music and generative arts, but as a cellist and as someone who played music with people, I thought this is quite a cool kind of compositional model. This could be quite nice. So that my work early on focused on that. In fact, I'll give you a little example. So I called it Alice and Herself Karaoke Machines. So it's basically kind of generative folktronica. It was using some models of homeostasis, other adaptive systems like neural oscillators, biological models that I sort of thought of as adaptive pattern generators. And everyone, I didn't realise how maxy you all were. There are a set of max objects made in 2002 that still run, which is quite amazing, that support this kind of interactive, generative, sort of adaptive approaches to human-machine interaction, if you like. I also thought quite a bit about theorising interaction around that time, so thinking about the difference between growing up playing a cello and being sort of adaptive towards my instrument versus building instruments that we constantly sort of interact with and adapt to and learn from, like Lauren's idea of this, very long-term interactions with our instruments. It's an ongoing process. So there's a whole bunch of work around that, which I'm not going to dive into now, just to sort of flag so you understand the context of my thinking a little bit. Whilst I was, during that time, during my master's, thinking about looking at these formal models of adaptive behaviour and thinking about these things in the real world, I came across this article in a really kind of hippie journal by this guy, Bernie Krause, who some of you may know. He was a Moog player. I think he played in the Doors even, and then he studied bioacoustics, and he became he spent a lot of time, thousands and thousands of hours, recording in pristine habitats. So in savannas and in mountains and in jungles. And at the time, back in the 90s, the idea was that the dawn chorus was a cacophony, right? It was noise, essentially. And he said, from his experience being in these places, he said, no, the dawn chorus isn't a cacophony. It's orchestrated. It's this beautifully orchestrated piece, if you like. So he came up with this idea of the acoustic niche. So what he was saying here is that certain species, if they're in a stable habitat for a long time, their calls will kind of evolve to kind of fit round each other, if you like. And we're going to come back to this idea. But at that time, so this is like 2002-ish, so I was thinking about ways sort of generative composition, if you like, ways to orchestrate different parts together rather than through the rules of harmony or improvising, these kind of abstract metaphors. And I was quite naive to all of, as I say, generative art and all the sort of 1950s composers that had explored these ideas. So being a good artificial life student, I made an agent-based model of this to see if that could work. So very, very simple model where you have a population of agents that sit in kind of pitch time space. So they're literally just like an integer array with a pitch and a time, right? And they can only mate if they can hear something. So they occupy the same pitch time niche as exactly one other, right? So they're not, it's a bit like a cellular automata idea. It's not overcrowded, but they can see each other. And through that simple algorithm, we evolve, I can't remember how many generations this is, we evolved to see these clusters of little groups occupying unique kind of pitch time slots. So it's like a little exercise I did, I think it was part of my master's or PhD, I can't remember. But I didn't really pick it up, but it sort of stuck with me, if you like. I worked with, between 2007, 2009, I went over to Australia to work with John Mccormick, who's in evolutionary generative art, mostly working in video stuff. So he was quite a pioneer of early 3D procedural graphics. So back in the 1990s, he was making procedural worlds of these beautiful ornate sort of flowers and forest and organic structures. So we shared this interest, it's sort of between being in artificial life and this sort of obsession with open-endedness and how can we get open-ended evolution in silico. Then in generative arts, it sort of translates to, well, how can we get kind of diversity? So in behaviours, in structures, synchronic sort of diversity here and now, and diversity over time in temporal media, so video and music. And thinking about what was common then in evolutionary, if anyone uses evolutionary algorithms, you know, you either set a fitness function, right, be like this, or you have interactive evolution where you say, oh, I like that one, let's breed, right? But if you think about the reality in the world, that's not what happens. Fitness is implicit, right? Fitness is like, can I survive now and have long enough to reproduce and confer some advantage on my offspring so that they can reproduce, right? So fitness is actually determined according to the environment now. There's not this like teleological future or this like hand of God coming in. So we were thinking about ways to define implicit fitness with what we called implicit fitness without having to interactively decide or set this kind of formal fitness function. Yeah, and one way to do that is to take inspiration from nature and actually hook up. If you think about standard genetic algorithms, there's no sense of environment, right? They're just it's like a bunch of arrays, isn't it? We make a class. They're not embedded in an environment somehow. And actually, if you think about it, that's what's key, is this coupling between the agents and the environments. And as soon as you make this feedback between the agents and the environments, then you start to see some diversity. You start to see some variation, like speciation in the agents, and then some heterogeneity in the environment. And that's that kind of key feedback is where you get this kind of diversity from. Now, one way to do that is to kind of take inspiration from nature and make a sort of abstract energy model, if you like. So most even in a life world, things might have energy, but it was like this half. So agents got energy and they could survive for a bit, and they had to do some stuff in the world like move an object or do this, whatever this, and some kind of activity, and then they survived. But actually, in the world, we've got recycling, right? This part is never modelled. This part where you basically eat shit, if I'm honest. So you've got detritivores and microorganisms, and you recycle stuff. And this energy recycling is actually incredibly powerful in a kind of algorithmic sense. So there's about I don't know, about a dozen or more little sketches we made, which are all online. If anyone's interested in this kind of stuff, exploring these ideas. Here's an example in another sort of sonic ecosystem, if you like. So this is it's called Scape, and the game we played was like, what's the minimal model we can define with the most complex range of behaviours, yeah? And then let's manipulate things like heterogeneity in the environment to see what's going on. So in this world, these little agents, they can be various sizes, as you can see, and the game is you can suck energy in from below, and this is a filter. This is just like a spectral filter, yeah? You can suck energy in from below, and then you spit it out. They're little arms, so they suck energy in from one bin, and then they spit it out in another bin, yeah? So you're basically like transferring frequency, spectral energy to another frequency band, right? And that's kind of it. There's the rules are really simple. You suck in energy. If you get up to a certain threshold, then you reproduce asexually. So you reproduce, you split in half, you mutate a little bit. And there's a few things I didn't really think about, like there's no wraparound, yeah. So what actually you get some quite interesting kind of evolutionary survival strategies emerging. So these guys have all worked out if they hang around on the edge, it's not wraparound, it's reflected. So I can actually feed myself. If I get it right, I can like sit here and like loiter at the end and feed myself. Or they can hang around in clusters and kind of feed each other if they evolve to have the right size arms, if you like, backwards and forwards. And then what we notice as well, so the red stuff is energy that's sort of coming in from the sun, right? And you'll notice it's stochastic. If you put it flat, this doesn't happen. We don't get this variation. If we have this more random distribution of energy, creating like heterogeneity in the environment, this guy's just the last remaining population, so all this energy is building up, and they hang around because it's safest to be here. The small ones don't use so much energy, so they can survive longer, and we're just going to hang in, and then we get a massive population explosion. Yeah, so we see some really quite complex dynamics, both in terms of the population dynamics and the kind of behaviours that we get, right? So none of this is programmed in. These strategies are all kind of emergent. So this was, we spent a couple of years, and it all got sort of disappeared up my own arse a little bit, to be honest, playing with these things. And there's maybe some useful insights there for people building interactive arts. And it made me think more and more about this idea of kind of sound as a resource and these sort of sonic systems. So enough of that. There's lots and lots of them if people are interested. So I'm going to jump forward a little bit, and just so that sort of closes the early generative art stuff in silico. I'm going to drop in some work I'm doing now, which is sort of a direct response to that, really getting fed up with working symbolically and wanting to make systems in the world, so vibrating systems. So I'm currently working on a Feedback Cello project, and I'm actually currently committed to no computation at all. There is a teensy in the loop, and I've taken it out at the moment. I'm just exploring a purely analog system. What I learned from all that work with agent-based ecosystems is that this feedback is the most important thing, right? This feedback coupling between the thing and the world is where we get our richness from. I think everybody here knows that. And so for me as a cellist, then that's quite a nice idea to make a feedback cello. What does that mean? Well, you get a normal cello, you put some pickups under the strings, you chop a hole in the back and bolt a speaker on, so you've got a transducer on the back, and then rather than, you're basically flipping the cello on its head, right? Rather than injecting energy from your arm to make the strings resonate, once you turn that on, even as I say at the moment, I'm committed to purely analog, so I literally just have this going through a mixer. Then the mixer amplifies any sound. The pickups pick up the vibrations of the strings, they're amplified, it makes the transducer vibrate, that vibrates the cello body, that goes up through the bridge and it vibrates the strings, so on and so forth. Yeah? So we get this self-resonating system. And it's very much like all the stuff that like LuCeRNEM people were exploring, but rather than like music on a long thin wire in a room, or I'm sitting in a room exploring the resonances of the room, we've now got 4 or 6 strings, which are sort of oscillators, but they're also filters, to coming to like Owen's ways of thinking. So the strings are filtering the system as well as being the sound producing device. So we can get these quite complex behaviours. The system self-oscillates. So this is me controlling the gains manually, and I can get each of the independent strings to oscillate. And there's some really interesting things harmonically going on here, depending on the tunings, right? Things will either reinforce or kind of compete and suppress those oscillations. So you can get, I'm going to skip through this really quickly, but I'd love to talk to anyone working in this area later on. You can get some quite nice new sounds that you can't normally get. Now what you're doing is sort of surfing this instrument that's live normally in itself, if you like. So you've got this like, you've got these almost sort of like multiphonic. So this is a trio with a drummer and a saxophonist. Like normally as a cellist, I can't get in the sound world with a saxophonist and a drummer, right? But with this instrument, I've got this sort of range of different sounds that I can play with. So it supports thinking about different other ways to close that loop. This is just, playing with contact mics and kind of thinking about the modal resonances. Suddenly it makes me aware of the modal resonances of my cello that I wasn't before. This is Chris Kiefer that the project is a collaboration with. It also can make quite brutal screams. So Chris's cello does have a Teensy on board going through Super Collider, and he's processing the strings so that the strings then become a controller, really, to a sort of weird hybrid synth. So one reason I wanted to mention this is partly because it's what I'm working on right now in parallel with the other stuff that I'll mention in a sec, partly because I think some of you might be into new instrument making, and partly because it illustrates one of the sort of key premises which I realise guides everything for me at the moment, and which maybe is useful to you as well, which is this idea that this sort of work we explore very intuitively, and we kind of come to trust our experience of what works or what doesn't work. But then there's also a time to stop and say, well, but is that real, if you like? So for us, we feel like these are complex dynamical systems in the truest sense of the word, that the kind of good shit happens on the edge, if you like, in that sort of on the edge of complexity type idea, that these feel like there's this, like in the artificial ecosystems, there's this sort of cycling of energy, and we're riding and changing this system, and that there's these, that the strings can maybe be thought of as different attractors that are sort of channeling or focusing the energy as it flows around the system. So that's quite useful language for us as feedback musicians. And in some ways, I feel like if the language works and the music works, that's fine. But at some point, if you're building and being an engineer, then you want to check, like, does the language actually stand up to, can the language then help drive the next round of development, if you like? So some of the work we're doing at the moment is applying the tools of dynamical systems thinking, so complex systems, measurements, so typical things like doing phase portraits. So this is when the top string is like in simple harmonic motion. The second string is sort of slightly coupled, so it's in its sort of base frequency, its fundamental frequency, if you like, but being messed around a little bit. The third string here was quite heavily modulated by the other two, and we can see this. They're not like strange attractors, but we've got these more complex attractors, and the fourth string was really being like judded around. So that was. Is
that the same moment? The fourth string?
Yeah, this is at the same moment. Yeah. So it was mostly just a test in like, does our intuitive feeling of this in terms of attractors like actually marry up with if we make a phase portrait? And what we're working on at the moment is thinking about this sense of sort of agency and otherness in the cellos. It feels like the strings are kind of pulling at each other and like influencing each other, which is why we don't have so much influence on the system. So we're using some of these tools from neuroscience to look at whether there is actually coupling between the strings. Like, does one string actually predict, if you like, the future of the next strings? And for people interested in once you've got these sorts of time series analyses, then you can also do that maybe, I don't know, I'm going to have a go, between your brain and the instrument, right? Because in these algorithms, it's just a time series. It doesn't matter whether it's the string. So we're doing this on RMS, done in the spectral domain of each string, or whether it's on your heart rate variability or an EEG, so on and so forth. So this is very much in process. These are the sorts of results we're getting. So we're getting some. Actually, I'm not even going to go into this because I want to get on to the other stuff. But if you're interested, I'd love to talk to you about this sort of stuff later on. The final close of that bit is to say we've then, as well as so these feedback instruments, so the feedback couples the strings and makes this self-resonating instrument, which then you, when you're playing, can be thought of in this feedback loop with it. So then, just for kicks, we've made this is the music department house band. So it's me and Chris Kiefer on feedback cello, Thanos, who's an ex-PhD student, on feedback double bass, and Thor Magnusson, some of you may know, on phonoscope. So we basically, we just call it acoustic networking. So we basically put Thor's phonoscope signals into our instruments as well as them coming back in themselves. So, and we make this sort of spectral drone music where none of us really know what's going on, basically. We're called the Brain Dead Ensemble, and we released our first album earlier this year. So it's quite a nice, again, intuitive reflection on what happens when you're not in control. Actually, you have to enter this sort of brainless state, if you like. Okay, so that was the work in above the line, if you like. So thinking about systems kind of inspired by natural systems and complex systems for performance. And then in the rest of the talk, I want to talk about this work in ecoacoustics. So thinking about how we might be able to listen to biodiversity and then get a little bit critical. And this was Owen's idea. Owen was part of a network that I ran called Humanizing Algorithmic Listening, and thinking what it means to kind of trust our tools, if you like. What does it mean to use machine listening and fairly complex abstract multivariate modeling to infer something about the world? And I'm going to run out of time a little bit, so I'm just going to judge your faces and see which bits we need to elaborate on or not. So this comes right back to this idea of the acoustic niche, this Bernie Krause guy. It sort of stuck around in my head, and I was thinking about it maybe around 2012 maybe as an art installation. Could we make an agent-based system that kind of grew into the cracks in real-world ecosystems? So if you imagine a black box with an evolutionary agent-based system sitting at King's Cross, and it had to evolve to fill the gaps, versus sitting in the Yorkshire Dales, then you'd get this population that was sort of like the imprint. So I was thinking about, like, a photograph has a negative, a 3D form has a mould. What's the inverse of a soundscape? What are the gaps? Can we kind of make this compositional system to fill the gaps? And then I bumped into my old capoeira teacher in a cafe, who's a conservation biologist, so he's concerned with saving species. He was working in Ecuador trying to save the last remaining population of the brown-headed spider monkey. But to save the species, you need to save the forests, right? And to save the forests, you need to give the people that live in the forests another way of earning money so they don't chop down the trees. And in order to then get some money for your whole project, you need to show that your project is working. You need to monitor the success of your project. You need to monitor biodiversity, right? And monitor I don't think I need to tell you all, monitoring biodiversity is pretty critical. We're all quite hung up on carbon, reducing our carbon emissions, but actually biodiversity loss is like, 1,000 times above base rate at the moment. We've killed something like 83% of mammals in the last 20 years or something. And this matters because, existentially it's hard for us to deal with, but actually our ecosystems might collapse. We need our ecosystems for air, water, those kind of basic things, right? So there's a whole bunch of multilateral initiatives to support biodiversity and increase and preserve and reverse biodiversity loss in cities as well as in forests. But we can only do that if we can measure biodiversity. Now, how the hell do you measure biodiversity in the Amazon, right? Traditionally, Well, let's stop and think for a moment what biodiversity means. Biodiversity is not like a measure, it's not like an SI unit like length or weight. It's some measure of the number and range of species in a particular time at a particular place. Yeah? So traditionally biologists put on their wellies and they count the birds and the bees and they measure moss and trees and they tally all that up in a nice kind of histogram bar chart like this. So this is the number of different species heard at 10 minutes in the cloud forest in Ecuador, and this is the abundance of each one, and this is the number of species. And then ecologists do a bit of maths on that bar chart because they want a single number, yeah? So you might count the number of categories, that's richness. You might find that kind of average abundance, which is the mean of the height of those. Or they work a lot with Shannon entropy, which I think is probably familiar to you. So a measure, basically an entropy measure of the distribution of that chart, right? So that's all really familiar. That's how it works now, but there's not enough people to stand in all the forests. And in the places where we need this most, nobody knows what the species are, okay? So this idea of listening can be really useful. If we think it through, if things need to communicate to breed, yeah? If you can't hear each other because there's too much traffic or there's other species in the way, then you can't mate and then your species will die out. And if you can hear each other and you do mate, then your species will sound a little bit like you. Yeah, so evolution kind of self-organises the soundscape. So we get this well-mixed, this well-arranged, this good arrangement like an orchestral arrangement or a well-mixed dance track. We make space for each voice, right? And if that's the case, then that structure should tell us something about the state of the ecosystem. Yeah, I think that makes sense. And this is what we hear. So this is in Ecuador. So the frogs are all down the bottom here. We've got Orthoptera, grasshoppers, crickets. You could hear the cicadas, that's kind of and then there's some bats that none of us will be able to hear because all the top end of our hearing's gone. So ecoacoustics, bioacoustics, right, is studying the sounds of individuals and then using machine listening maybe to identify their calls, template matching or supervised, unsupervised clustering. What ecoacoustics is doing is saying we're not interested in like instrument classification, we're interested in how good an arrangement is this, how good is this orchestral arrangement. We're thinking at the community level and we're thinking about the whole soundscape, right? So the kind of research question is, well, what sort of machine listening features might we use to access some of these ideas, some of these ecologically meaningful measures of ecology? So the last few years I've been working in Ecuadorian Amazon and in UK forests, in the Arctic looking at wilderness mapping, and in Indonesia looking at reef monitoring, to try and look for these different ways of exploring this. So this is really muddy and kind of wet work in a way, and then it's a mix of that very muddy field work and kind of equally muddy multivariate stats trying to make sense of everything you do. So in the last few minutes, I want to if I was giving an ecology talk, I'd tell you about how we were gathering all this data and how we calculated all these different audio features. Ecologists call them indices. And then I'd show you that we had great correlations in all our models, had very low error, and isn't that brilliant, right? But actually, there's a bit of a problem because that is true, but the problem is, to do this work, you necessarily collect so much data that when you come back to interpret your model, you can't go back to the data to listen to it to work out what the hell was going on, right? So we've got this kind of impasse where we need like terabytes of data because ecological data is really freaking noisy, but then we can't really make sense of our results. So it's not like a machine listening classification task where we go, here's some drum hits. Is it a cymbal? Is it a ride? Is it a snare? Yes, it is. No, it isn't, right? And we can go back and check, was that prediction correct? Because we're only just starting to really understand the fact that sound is a resource, the fact that sound matters to organisms. We're only just starting to appreciate that like sea kelp is sensitive to ocean noise, that coral polyps and fish larvae use the sound of the reef to navigate back home. Before they can sense light, they can sense vibrations. We're only just understanding that like certain species of bats and plants have co-evolved because this particular fly-eating plant was shit at catching flies, so it needed to do something else to get protein. So it evolved to be like an acoustic, basically focus the sound of bats, so the bats came and slept in the flower and pooed in there at night to give it some protein. And we're only just realising that flowers don't attract insects by virtue of being colourful. They actually work like little dishes to focus the buzz of the insects, and as buzzing insects come past, they increase their sugar in their nectar, right? So we're suddenly realizing that sound really matters to loads and loads of species, and the possibilities of using machine listening, right? So if you think about it, sound is like can capture the really intimate moment-to-moment dynamics of living creatures. But we can do this potentially at scale, yeah? We can make little tiny microprocessors now, and we could drop them all over the Amazon and collect all this data. These projects are going on. So there's a huge project in Australia where they're just recording all the time forever now. But like, what the hell are we going to do with this data? Yeah, there's another sort of hours talk here. But I think you all sort of get where we're at. Even if we want to validate this approach, right, then we collect some new indices and we compare it to a ground truth, which might be the number of species, right, that we counted in the same data. And then we make a model, and as I said, then we need to interpret it. So I'm going to whiz through all of these slides. You'll quickly see the sort of work it is. You go to these places and you collect data and you record stuff, and you get a feeling for what's going on. I'm going to flick through all of it. Then there was a deviation on PLCA because you're all into your non-negative matrix factorization, but we can, again, I'm going to skip through that. I was saying to PA, sometimes I have no slides, and this time I think there's about 120. So what I want to point out is this. So here's an example of what I mean. So this was our data that we collected to look at, can we use audio features, and actually some really simple things like RMS, ZCR, entropy of the frequency domain of the frequency spectrum. Can we predict the range of species and the habitat that those species live in from these? And we can do a regression. So I use multivariate random forests because they allow us to use a huge range of parameters and test a range of inputs, if you like, without getting some of the other ecological models get a bit upset by that. And we can do regression models, and we can also do clustering models. So this is probably a format you're all familiar with, confusion matrices. So which way around is it? Columns. The actual columns are in columns, and the predicted are in rows, right? So this is in the UK. This is the actual bird species that were named. So 1 minute audio files, listen to them all. There was like 2,500 in each habitat. Listen to them all, name the species, run up a bunch of acoustic indices, audio features, and then see how well they predict each of the habitats. So we record it in old primary forest in Ecuador, secondary forest, so sort of regrowth, and then palm oil plantation, and the same in the UK. So very roughly, the blacker the diagonal, the better, right? And the whiter the off diagonal, the better. So if we just compare species, which is our ground truth, right, to the acoustic indices, this is in the UK, this is in Ecuador. So particularly in Ecuador, our acoustic indices, right, these numbers are lower. So it means that the acoustic indices actually better predicted the habitat type than the ground truth, than the species themselves. So it's like, wow, that's amazing. And my ecologist friend went, wow, that's amazing. So sound is like better than species for measuring biodiversity. And I was like, well, it might be, but there might have just been like a tractor here at 6 o'clock every morning, or there might have been someone working in the palm oil plantation with their radio on every day. We don't know, right? The point is we don't know because there was like 175,000 files here, and I can't go back and listen to them. So this is what I wanted to put to you at this point is, this is all great. We can do things like do PCAs and have a look. Does it kind of make sense? Do the species make sense, according to our intuition? So I'll slow down a little bit then and highlight then that there's what I'll come to at the end, there's sort of 3 open problems here, and deciding which features to use is obviously one of them. So we noted in a big hurry that one approach, so some of you might know Dan Stowell. So one of the approaches is the sort of Dan Stowell approach, which is let's develop deep learning to recognise individual species calls, right? And that's very cool. And he's done some amazing, and that whole world has done some amazing work in the last few years. And a lot of ecologists like that approach. If you're trying to monitor an endangered species, especially if it's got a really particular call, which some of them do, then that's brilliant, right? You can now build those models, and they're getting cheaper and cheaper. You can maybe even use them on embedded systems. So you literally have the system in the field and it counts. I heard one whoop whoop bird this morning, so on and so forth. So that's cool in some situations, but in places where often the most important places, the biodiversity hotspots, it's so freaking complex. There's so many species and so much variation that even the bird species, there might be like one person in a particular area of Ecuador or Brazil that knows those species, because there's so much variation, right? And if you think about insect species, which are also incredible indicators, nobody knows how many species there are. Nobody knows what sound those species makes. So freshwater ecoacoustics is emerging now. There's loads of noise that happens in freshwater. No one's got any idea what it is. Even in the sea, we're starting to understand all these fish make crazy noises, and I've got some examples that I've got no idea what they are. Some of them are swim bladder, kind of farty noises. And some of them are just sound like mermaids. I mean, I've no idea, what these things are. So in places where we don't know what's making the sound, then we can't do deep learning, right? We can't label a data set. This individual-based approach doesn't work. So we need to have these kind of zoomed-out community-level indices. So the first sort of generation of indices, and you can see how new this field is. This is the first generation happening like 2011, 2012. People, you remember I showed you that like how do we get from our bar chart of species distribution and boil that down into a number. That's the way ecologists work. So they kind of did the same thing with their indices. They might say, for example, well, the health of a habitat is like how many birds there are to how many cars there are. So they made a normalized different sound index, because they're used to working with normalized different indices for snow cover and ground cover and these kind of things. And that's basically a power spectral density estimate divided into low frequency, because that's where cars and planes are, right? Except they're not, because they have a lot of high end as well, so it doesn't really work. And then high end biophony, because birds make higher frequency, don't they? Except they don't. A lot of them make low frequency. So there's some of these are very intuitively designed, but they don't really stand up. So a lot of them are then also based on Shannon and Gini entropy applied to a bin spectrogram. So you do an FFT, you bin up the magnitudes, and typically they split the frequency range of interest into 10. Why? 10's a nice number, isn't it? It's just like, okay. And then they do entropy on it. So the idea in ecology, which also doesn't really work, it's like if you have one species dominating, then that's not great, and a flat distribution of species is a more healthy ecosystem. But in itself, that's nonsense, right? Because you have apex carnivores and predators. You have one puma for every 4 million field mice. They don't live in the same, but you get the idea, like different things on different levels. And when you apply that to sound, they're saying a flat distribution, so equally distributed energy across the spectrum, is a sign that everything's self-organized and all these there's loads of creatures in healthy habitat. Or if you're working in the field with really, really robust microphones with a really high noise floor, it's silence, because that's also a flat spectrum, right? So there's a few problems with some of these indices, which makes them really hard to interpret. But they kind of do work as well. If you say things like, just what is the overall sort of range? So this is a really kind of cack-handed one that says so do a mean spectrum and then take away the band with the lowest amount, and that's probably your noise floor. So it's really, really crude. And then what's the remaining area under it? That's called the Bioacoustic Index. Actually, that's not bad. It does quite a good job of saying what's the overall sort of sound happening in that world. But for the first sort of 5 years, all these ecologists went off and made up these indices, but they didn't even look in music. information retrieval, right? And even the simplest ones. So we also tested just the most simplest, like spectral centroid, RMS, ZCR, these kind of things, which are surprisingly powerful. But it's not a celebrating ecoacoustics conference, so I'm not going to go into the details of those. Do you want a little bit of Bregman as a sidestep? Okay. So when I first came into this field, then, as a musician, totally naive to ecology, but except in the abstract sense, I got quite excited, as I say, about this idea of this acoustic niche, this idea that kind of things self-organise, and they're kind of, you know, these voices sort of organise themselves around each other. So but then all of these things are like, okay, and now we'll work in the time domain or the frequency domain. And I was like, but, you know, if there is such a thing as an acoustic niche, it's not in the time domain or in the frequency domain. It's like some like beautiful dance through some like abstract high dimensional space that crosses across these domains, right? So I didn't really know, I didn't really have the expertise, but it sort of smelled right to think about time frequency domain, right? So I went off and sort of started looking at various ways of doing that, basically. And the PLCA stuff, so you're all massively into NMF. So PLCA's principal latent component analysis is basically saying, like, if stuff moves together, it probably belongs to the same thing, and we can separate out the spectral template, if you like, from the temporal template. So if we're listening to a piano and we play a scale on the piano, each of those notes will be separate in time, but they'll have the same spectral profile. So we can separate out the time they happened from their spectral information, if you like. And I knew, some of you all know the illustrious Michael Casey, who used to be at Goldsmiths, so I knew when he was at Goldsmiths. He's now over in Dartmouth, and I thought, who do I know in the world that knows the best about this stuff? And I thought, Michael Casey. So I emailed Michael and said, I've just got this hunch. I'm thinking about well-structured soundscapes and what that might mean. And I think there might be a way to use kind of source separation models, but not to separate the sources, but as this kind of weird proxy for how well structured are they. Yeah. If you got a Beethoven string quartet and did source separation on that, it would be relatively easy to pull apart the voices. Actually, maybe that's a shit example. So Madonna Song, which I think was the first thing I heard Michael demonstrate this with. So the vocal line and the drum part and the keyboard parts are quite easy to pull apart because it's been produced so that each thing sits in its own voice, right? Like drunk people playing djembes, really, really hard to separate because it's all meshed up. It's all the same sound. They're not listening to each other. They're all playing on top of each other, right? So I was thinking similar thing in a primary forest. You've probably got not very many. Oh, there's a sound. Oh, you are. In the primary forest, you've got not very many birds calling, and quite a lot of space between them. Yeah. In the secondary, you've got this. So this means, by definition, a mixture of habitats, some primary and some farmland coming together. We've got a bit more raw because we've got less trees, less reverb. We've got a bit more raw from the open space. We've got some more species. We've still got the same species, but there's a few others coming in. And then in the completely open land, the silver pasture, we've got this big raw background noise, and we've got a whole bunch more species. So my prediction was, right, I don't actually want to separate out these voices and identify them. I just want to know how easily separable are they, yeah? So I managed to snatch Michael's mind for one Easter bank holiday weekend and get him to, this was before this stuff had been released. So this is what's nice about his algorithms is its shift invariant principal latent component analysis, right? So so you don't even have to have an exactly matched patterns. They can basically be, so he was looking at groove estimation, but birds are sort of periodic, but they're not completely on a grid. So you need this shift invariant stuff. So I had a look. I was interested then comparing, could these traditional indices separate out these three types of habitats? Is there a pattern between black, grey and white? No, not really. That's all you need to know. Is there some difference first of all, does this PLCA, so this is just working on 1 minute, and he's just taking like some sections of that. I think I gave him a 10-minute file, and then looking at reconstructions from the original, right? So from the spectrogram, it looks pretty. I'm really sorry, this was quite a long time ago, and I've lost the notebooks, so I couldn't find the audio. But you can see it's pretty convincing approximations. Now, any of you, there really isn't time to go into this, but if those of you that are familiar with this idea, so I get it conceptually. I didn't have the sort of mojo or the chops to implement this. So this is using Michael's libraries. Quite often I don't know how it works in NMF, but in here you can tune the priors, or you can set that you can use a Dirichlet prior, so it automatically prunes the number of components returned, right? And so rather than having a set, like rather than saying decompose this into 8 components for me, it automatically tunes and says these are the best X components, these are the best N components. So for me, I was interested in, does that N, I don't care about any of all the really complex heavy maths you've done, I just want to know how many components you think there are sensibly in this file, right? So if we look, this is in the primary forest, so this is time frequency and activation functions, right, which give us our individual reconstructions. So looking at these reconstructions, this is saying there's 4 fundamental things, right? Background noise. And are these separate species? I don't think they are, but they're quite clean, separate components, and the approximation is pretty good to the original. So that's what I was interested in, is like this K, this number of components returned. If we look at the secondary forest, then we had more voices there, right? We've got this background noise, and we've got these other, starting to see these sort of separated out distinct patterns. Again, it's a decent approximation. We've got 7 components returned. And then if we look in the silvopasture, we've got 6 returned with this great big background noise that we could hear. And then we're getting this sort of separation of different species very, very, very roughly. So a kind of total abuse of this algorithm, but to provide a sort of proxy of how easily, if you like, it can be separated. But this was maybe 4 years ago, and actually just this summer while I was on fieldwork in Indonesia, getting really baffled by the kind of crackling noise of the reef, and then these fish vocalizations that were quite distinct, and quite wanting to be able to pull them apart and thinking, I wish I had the chops to do that code, because I don't have that code anymore. Someone popped up from a research institute in Brazil and said, I've just read your paper and implemented a version in it, and it's really good, and would you like to collaborate? So I've now got someone actually who's implemented this really, really well, which in reef modelling works brilliantly, because you can separate the crackle of the reef from the fish really easily. That was actually a whole big detour of like how we can abuse algorithms in different ways. I'm going to try and swing, and if you want, this is all available now, this code. But I think people here are probably familiar with with Michael's Bregman lab stuff anyway. And this was a really hand-wavy paper that I wrote when I first came into the field, sort of saying, oh no, you don't want to do it like that. What you want to do is do this, with no results in at all, but people really liked it. So, breathe for a moment, and then we're just going to come back to this idea. So we're going to drop all of that PLCA stuff, because what we really want actually is some really cheap tools that we can run. Like now we've got recorders that are like this big. They run on really small batteries, maybe even on a solar panel. But we need all the computation to be very cheap, so that those batteries last a long time, right? And if we get it right, then we can give this to communities, really on the front line of climate change, and they can use these methods with their kind of lived experience of what these worlds sound like and what this sound means. Okay, so we're going back to these really cheap, like RMS, ZCR, so on and so forth, and we're remembering that confusion matrix where we had somehow better results. So the acoustic indices were more predictive of the habitats than the species were. So the ecologists went, woohoo, and I went, I'm not sure about this. Okay, because what we're getting to is this point where if you think what we've done, we've assumed this ecological community that we want to know something about. It's only a subset of of those guys that make a sound. So there's this acoustic community that we're recording, but then there's also the other things, the birds and as well as the birds, there's the planes and the rivers and all that kind of stuff. We're making a digital recording, and then we're extracting some audio features, and then we make inevitably a pretty complex multivariate model, and then we're kind of looking at the mean squared area or the out of bag errors, that kind of stuff on that model, and then we might plot it, right? So what we're working with in our papers is this sort of graphical representation of this pretty complex model, which is made on these abstractions of this audio recording that sort of maybe summarises some aspect of the thing that we're interested in. So we're quite far away, right? It's not exactly black, but it's pretty freaking grey. And trying to understand what that means is really difficult. And why I thought it might be useful to talk to all of you lot is partly because you maybe have the reverse problem where you've got quite small data sets, right? And your models are telling you something, but it's like, maybe that works now. So if you're doing like gesture recognition, that's kind of good enough. Except in the gig, it just totally fails. And you're like, oh, balls, why was that? And it might be that the model had got hold of some kind of regularity in your data that wasn't what you thought was important, yeah? So I don't know, some of you might even know Bob Sturm. He's written about this really nicely in terms of horses, which is a whole nother talk. But he's developed some ways to kind of empirically test whether there's this sort of confounding variable in our machine learning models, if you like. So this is a huge problem for ecoacoustics because, as I say, we're only just understanding what sound means. And one possible solution, and I'm gonna have to wrap up, but one of the reasons I want to speak to you guys is to come back to this idea, this mixture of kind of experience and experiential knowing, if you like, and kind of empirical knowing. And for me, like machine listening is this amazing bridge from the here and from this kind of intimate moment-to-moment dynamics to this zoomed out way to listen to the whole of an ecosystem, the whole of a forest or a whole of a reef. But no one person can do that, right? So what we need to try and bridge is this sort of distant listening and this close listening. And how can we know our data? Well, one way to know what something means is to just experience it forever. So like Bernie Krause, who spent thousands of hours, but we've said we can't. Another way, this is referencing Bob Sturm's horse paper, which we can talk about if people are interested, but not now, is saying, well, is what my model says real? Does my model care about the same things to over-anthropomorphize it? Are the regularities that my model's held on to, are they the things that I care about in the world? Yeah, and he's developed this really nice way to test that. Another way is to develop new visualization techniques. So this is a lab in Queensland working on this. So this, instead of being a spectrogram, is a false color spectrogram. So you basically take 3 indices and then map RGB. So each pixel is a 1-minute sound file. And then you can look at, this is a day-long recording. So you can see like the dawn chorus kicking in at 6 o'clock. We don't quite know exactly what it means, but it's sort of giving us a rough idea. And we can do these with deal maps. We can do this like over a whole year. We can see the dawn chorus shifting as the sun changes. So these kind of ways are quite nice to get an overview. But what I'm really interested in talking to all you lot about is maybe other ways to more interactively, say, reperceptualize our features, so we can kind of really get to know. So we can kind of do feature surfing, if you like, in the same way as we know the feedback cello by surfing around on it. We can get a feel for our dynamics. So some thoughts how we might do this. Luc Dubois, you might know, he did this billboard back in 2000, I think it was. He's basically just like a mean spectrum of, and he did it for every #1 hit, like everyone does from 1950 to today or whatever. So you get this like soundtrack, right? That's actually quite cool. If you did that for each minute, of a 24-hour data set in like 15 recorders across a place, you could, and used either a VR headset or even just an accelerometer on a phone, you could kind of time zoom through data sets, and you could spatially move around in your spatial recordings in the field. So some ideas from like interactive art might be quite useful. Some of the stuff we've talked about, and I think we're going to be talking about in the next few days. Yeah, great. So I've been speaking to Demo Schwartz about his cat art system. Already is really useful for me. So how do we check the data integrity? Where are the outliers? I've collected all my data in. Actually, did some of the batteries run out? Was there a bear? Well, some of the stuff, there was literally a bear pissing on a microphone, right? That was quite a strange sound. It wasn't ecologically relevant. Well, it was, because there was a bear there. That was quite cool. But, you know, when we cluster things like this, we'll see straight away, was there silence? Is there distorted files? And we can rapidly sort of get to know. We could have really quite nice hacky things where this ring finger, do you know this? So you basically just like use your body conductors to plug in speakers. So you could then use sort of surround sound, like hacky surround sound techniques to kind of listen to different speakers and literally get an embodied kind of feel for it. So for me, the thought of doing this with like some Indonesian fishermen, for them to get to know their, it's quite exciting. Or you might have some solutions in your next work package, is what I'm hoping. Okay, so to wrap up, and I did warn you it was going to be like quite scattergun talk, but hopefully you had enough coffee. We can hear biodiversity, probably, but there's lots of open issues. We need some better basic features, and there's a whole range of tasks. We need probably some interactive tools to support data checking and interpretation, and we also need to widen access to frontline communities. So to come back to my little circle, what I'm thinking about next is maybe bringing in tools from participatory design, making some nice like web audio interfaces with community groups in a way that's meaningful to them, and at the same time then doing a kind of using that almost like an ethnography tool to understand, to bring to contemporary neuroscience their understandings of how reefs work. And the take home then might be borrowed unashamedly across disciplines, never trust your models, always trust your intuition and then measure it. And then yeah, come to this place where kind of experiential knowing and sort of empirical knowing, where they meet, then that's quite a cool place to be, I think. I put truth in there because we were talking about truth just now. Obviously, there's not really any truth anywhere. This is the team we must acknowledge. You don't do any of this on your own. So Mika Peck is a conservation biologist. Paola is an amazing PhD student who's now back in Ecuador. Matrices was a brilliant French machine listening. These guys did all the data labeling, and these guys did some of the data crunching.